Okay, so in this problem from the team challenge from class, we were given the following unbalanced reaction for photosynthesis. Water plus carbon dioxide in the presence of UV light produces sugar and oxygen gas. And the first thing we're asked to do is balance this reaction. So let's rewrite our reaction, leaving ourselves some space to write in coefficients as needed. The way I like to think through balancing reactions is to make the following table and to count how many of each type of atom appears on the reactant side of the arrow versus the product side of the arrow. So I'm going to save oxygen for last because oxygen actually appears in every single reactant and every single product of this reaction. So it's going to be the hardest to balance. So we'll start with the carbon. On the reactant side, we have 1 carbon in the carbon dioxide molecule, and on the product side, we have 6 carbons in the sugar molecule. In order to get these numbers to match on the reactant side and the product side, we can multiply the reactant side by 6, which is the same as putting a coefficient of 6 in front of the carbon dioxide. Now let's do the hydrogen. So on the reactant side, we have 2 hydrogens in the water molecule, and on the product side, we have 12 hydrogens in the sugar molecule. In order to get these two numbers to match, we can multiply the reactant side by 6, which is the same as putting a coefficient of 6 in front of the water molecule. Now let's count our oxygens. Remember that we've already put a coefficient of 6 in front of water and a coefficient of 6 in front of carbon dioxide. So we have 6 oxygens on the reactant side coming from the water, plus 12 oxygens coming from those 6 CO2 molecules. So altogether we have 18 oxygen atoms on the reactant side. If we go to the product side, we have 6 coming from the sugar and 6 coming from the oxygen. In order to balance this, we could multiply the oxygens to oxygen atoms by 6 to give us 6 plus 12, which does equal 18. So this is the same as putting a coefficient of 6 in front of the oxygen molecule. So our balanced reaction is 6 waters plus 6 carbon dioxides in the presence of UV light reacts to form 1 sugar and 6 oxygen. The next thing we were asked to do is express the rate of reaction relative to the sugar formation. If we look at our balanced reaction, sugar is a product, which means it's forming, so it will have a positive slope or positive rate. So it's going to have a positive sign in front. It has a coefficient of 1 in front of the sugar, so we're really thinking about 1 divided by 1, but that's just multiply by 1, so we can neglect to write that. And we'll have the change in the concentration of sugar divided by the change in time is our rate of sugar formation. And so this is going to be a 1-to-1 relationship to the rate of reaction. The last thing we were asked to do for this question was to explain how the rate of production of sugar is related to the rate of depletion of carbon dioxide. So carbon dioxide is a reactant, so it's going away. So let's start by writing our rate of sugar, which is just positive change in the concentration of sugar or the amount of sugar divided by the change in time. When we're thinking about writing our carbon dioxide, note that it's going to be negative because we're getting rid of carbon dioxide. So it's got a negative change. And we'll also divide by 6 because we have to account for the coefficient. Really, when we do this reaction, we're reacting 6 moles of carbon dioxide. So we have to account for the fact that there's 6 molecules or 6 moles. So we're going to divide by 6. And that will be multiplied by the change in carbon dioxide concentration divided by the change in time. Another question from the team challenge was looking at the rate law for this reaction. 2 ClO2 plus 2 hydroxide ions yields ClO3 minus plus ClO2 minus plus water. And we're told that the rate law is rate equals rate constant K times the concentration of ClO2 times the concentration of hydroxide ion or OH minus ion. And we're asked to find the units for the rate constant. So let's write our rate law out. And now below it, I'm going to write the units of each thing that will go with the numbers that go in this expression. So in green, we're going to show the units. The unit for rate is molarity per second because we're looking at the change in concentration divided by the change in time. So if we were measuring a really slow reaction, such as the crystal violet reaction that you're looking at in lab, you're probably not measuring in seconds. You might be measuring in minutes, or even hours or days or years. But let's assume that our time unit is seconds for now. So we have molarity per second, which is what we were given up here in the problem. Molarity per second. Remember that molarity is moles per liter. We don't know the units of K, so we'll leave a question mark there. That's what we're trying to find out. What are the units of ClO2 in brackets? What do the brackets mean? So the brackets, if you haven't seen that notation before, brackets always indicate molarity or concentration. So this is capital N, that moles per liter. And the OH minus is also going to be molarity units. And since neither one of these has above first order, right, both of these are really, we can think about having a sneaky hidden little 1 up here that we're not writing. So they're both first order. This is molarity to the first power and molarity to the first power. If these were second order, we'd have molarity squared for each of them. But these are first order. And so now let's see if we can't solve for our units. So we know that molarity per second has to equal some unit x, which is the units for the rate constant, times molarity from our equation above. Or we can rewrite the right-hand side as x times molarity squared, because we can combine those two molarities. How are we going to solve for x and get x by itself? We could divide both sides by molarity squared, which is the same as multiplying by 1 over molarity squared. If we do that, on the left side, we'll have 1 over molarity times seconds, and on the right side, we'll get rid of molarity squared altogether and be left with x. Since x represents the units of K, that means that 1 over molarity times seconds are the units of the rate constant for this particular rate law.